Hi, my name is Shakeh Kalantarmoradian. This is my fourth year as an electrical engineering student at UCLA. This summer, I've been working at the Communication Systems Lab of Dr. Wessel, and my daily lab supervisor is Alex Balda. The research that we've been working on is called Analysis of Frame Error Rate and Bit Error Rate of Viterbi decoding with periodic puncturing. First, I want to give you a general overview of what our research is about. We analyzed trellis codes with periodic puncturing with additive white Gaussian noise added to them with signal to noise ratio. I'll explain what each of these terms mean in the upcoming slides. Understanding how puncturing affects the bit error rate and frame error rate is the main objective of our research. And our research is important because in the presence of noise, which is what we mean when we say errors occur, the information and data that are being transmitted get corrupted, and the desired message becomes noisy and unclear. Probably the simplest example that I can give you is a phone call. If there's noise in the transmission, then it'll be hard to transmit or receive the message. Previous literature has implemented the reliability output Viterbi algorithm ROVA with puncturing, which is the deletion of symbols before sending. And they did that to improve efficiency with incremental retransmissions and bit error rate union bound. What we would like to explore and add on to the previous work is to find how puncturing affects the bit error rate and frame error rate. Now I want to define some new terms that I use, such as trellis code and trellis diagram. A trellis code is a sliding window method of encoding a binary data stream as a sequence. Figure 1 shows a 4-state trellis diagram because we see 4 circles in each of these stages. And each of these binary numbers are representing the state. The green arrows correspond to input bit 0, and the orange arrows correspond to input bit 1. What is periodic puncturing? As mentioned earlier, puncturing is the deletion of symbols before sending. For example, if the pattern is 5, 1, so 1, 1, 1, 1, 1, that means we're sending 5 bits in a row. Now, if the pattern is 0 and 4 ones, then the first bit is punctured, meaning that we will not be sending the first bit, but we will be sending the next 4 bits. In addition to trellis diagram and periodic puncturing, I want to tell you about convolutional encoders and decoders. Convolutional encoder is a sequence of states with well-defined transitions between them. And a convolutional decoder is an algorithm that obtains the original sequence of input bits before convolutional encoding. For example, in figure 3, we see the encoded bits are 1, 1, 0, 1, shown in this red path because the bottom arrow is 1. So 1, 1, the top arrow is a 0, and the bottom one is a 1 again. In our project, our encoder takes a sequence of input bits and transforms them into a longer sequence of bits. Each encoder has a rate. The rate is k over n. K is the number of input bits, and n is the number of output symbols. In our research, we use a rate 1 over 3 encoder, which means it has 3 output bits per 1 input bit. Then the decoders take that inputted sequence, often with noise added to them, and they attempt to obtain the original input sequence fed into the encoders. And the last ingredient in our research that I need to tell you about is 8PSK, which stands for phase shift keying. The 8PSK constellation that's shown in figure 4 maps the 3-bit encoded sequence into X and Y coordinate system. For example, if the encoded bits is 0, 0, 1, they will be mapped to square root of 2 over 2 and square root of 2 over 2, assuming that the radius is 1. In our research, we used 2 codes called codes 13 and 14. Codes 13 and 14 are both rate 1 over 3 8PSK codes with period 5. In trellis codes for periodic erasures paper, that's the paper we used to start our research, and our research is based off of. Code 13 was designed to maximize sum of log of residual Euclidean distances for each periodic pattern considered in the channel. And code 14 was chosen because it had better performance compared to code 13 over progressive puncturing patterns only. And here's an example of progressive puncturing pattern. So if we start with 5 ones, we progressively puncture the first bit, then the third bit, then the fifth bit. Our tasks for this project are computing the bit error rate using two ways. So the first one is running simulations using our code and the data we obtained. And the second one is using the theoretical equation that was available to us and compare the two with each other and also compare codes 13 and 14. But what is a bit error rate? The number of errors per bits that have been altered due to noise, interference, or distortion is called a bit error rate. The theoretical equations that we've used are shown here. In this first equation, NB of A is just a constant for us that we obtained for each of the puncture patterns. RED is the residual Euclidean distance. That is a distinct value for each of the puncturing patterns and also each of the codes. 1 over N naught is the signal to noise ratio in our case, SNR. Q is the Q function. It's the tail distribution function of the standard normal distribution. And partial T partial I is the partial derivative of our transfer function. Now I'm going to show you a sample of our simulation and run videos. Here I'm using UCLA cluster 2 Huffman 2 cluster. The reason why we use this is because either we're not sure how many decodings we need, or we need a very large number of decodings, for example, 1 million. And our codes run much faster here compared to our local computers. Our codes sometimes take hours or even days to run. So you can see that I logged in. I uploaded my files right here. Now I'm writing the code to be able to run the code. And if I fast forward it, you can see that the code is running. Once this is done running, the output will be saved here as a .csv file. After that, we move on to MATLAB and we upload all our .csv files here to be able to plot. So here I'm showing my simulation plots. And then later on, we also have our theoretical equations implementation. And here are the results we got for our codes 13 on the left and 14 on the right-hand side. The x-axis is the signal to noise ratio. The units are in decibel, and the y-axis is the bit error rate. The solid lines in both figures represent the truncated union bound for each of these puncturing patterns. And the dashed lines are the union bound. We are currently working on the union bound for puncture patterns. And lastly, the lines with circles on them, they're the simulations using our code and the data that we obtain. We can see in both figures that the lines with circles converge to the solid lines as the SNRs get larger, which is what's expected. Our future tasks that we're currently working on are computing the frame error rate, FER, using simulations and theoretical equations as well. And what a frame error rate is that in a single decoding, if there are any bit errors at the end, we call that one frame error. One frame error can have many symbols and bit errors in it. And to conclude, we use C++, MATLAB, and Huffman 2 cluster software. We ran simulations to investigate the bit error rate. We've used the previous literature to compare our data simulations with the theoretical union bound for the BER under puncturing. Our results have allowed us to choose an encoding scheme based on its overall advantages, which is the lower BER compared to other codes, with the same puncturing pattern and same SNRs, signal to noise ratios. And we conclude that there are different constraints such as bit error rate or frame error rate that can be used to decide how a certain algorithm transmits data with the least amount of error and least number of input symbols. And here are my references. I'd like to thank the Communication Systems Lab, my PI, Dr. Russell, and my DLS, Alex Balda, for their support and guidance throughout this research. Thank you for listening.